In this video, we want to start taking a look at how you can start applying these linear functions and linear equations to some more real-world type problems. Now, of course, when you start getting into the word problems, these do start to get a little bit more difficult. So here are some quick tips that you can use so that hopefully this process gets a little bit better. First of all, you want to try and familiarize yourself with the problem as much as possible. This means if you have to draw a picture of the problem or just plug in some numbers to get a better idea of what's going on, go ahead and do so. The more information or the more you understand about the problem, usually the better it is. Also, try and work to translate the problem into math. Sometimes this involves either bringing up some additional formulas or trying to find connections among the pieces that you have. Then go ahead and try and solve the problem with the pieces that you've collected. Now, sometimes this actually yields a solution, and sometimes it doesn't. And if it doesn't, you may have to go all the way back to step one and see if there's anything you've missed as you've gone through the problem. Now, if it does look like you have a solution, don't forget to check that it makes sense in the context of the problem. Sometimes when you're working on a problem, maybe you're working with something like distance. If you have an answer that has a negative number, then you should be a little bit worried because you can't have a negative distance as your answer. And finally, once everything looks like it checks out pretty good, make sure that it translates back into English. Most of these problems are in a real-world type context, and so it should really fit in that context and make sense for the problem itself. So let's go ahead and take a look at one of our first problems. In this problem, we have that an anthropologist is using linear functions in order to estimate the height of a male or female given just the length of their humerus bone. Now, in order to make that connection, they use the following formula, that f of x equals 2.75x plus 71.48. Now, anytime you're given a function in a word problem, you want to start asking yourselves, what are the inputs that it uses and what are the outputs? If we continue reading the problem, it says that the height in centimeters of an adult female is given in terms of the length x in centimeters. So the way you translate that is that what you're given, the x, is your input. So if we give it some sort of length of the humerus in centimeters, it returns back to us the height of an adult female, also in centimeters. So now that we have a better sense of the inputs and outputs, we can go ahead and answer the question. A 26 centimeter humerus bone was uncovered in some ruins. Assuming that this was from a female, how tall is she? Since the length of the humerus bone is basically our input into this function, we're basically just going to substitute in what we have. So as you can see, I've taken that function and I've substituted in 26 centimeters. And now we go ahead and we try and simplify to see what the output is. After doing so, I get 142.98. And again, in the context of the problem, this is in centimeters. And so it's returning to us the height of that female, that she's about 142.98 centimeters tall. Now let's do a problem that requires just a little bit more work. In this one, we'll actually have to start looking for connections between some of the variables inside so that we can actually move forward and try and solve the problem. In this problem, we're going to be talking about two planes. The first one is a Boeing 737, and it has a cruising speed of 500 miles per hour. The other plane is known as a Dash 8, and it has a cruising speed of 302 miles per hour. Now suppose the Dash 8 takes off and travels at its cruising speed, so 302 miles per hour. And then 1 hour later, the Boeing 737 takes off and follows the same exact route. The question is, how long will it take the Boeing 737 to overtake the Dash 8? In a problem like this, you want to start recognizing that it's talking about distances and times, and so it might be helpful to bring in a formula that starts relating those things. So for this problem, I bring in the formula that distance is equal to the rate times time. And one way you could imagine this formula in practice is that if you know how fast you're going and you know how long that you've been traveling, this will compute your distance. So for example, if you're traveling at 50 miles an hour for 2 hours, it gives you a distance of 100 miles per hour. Now we're going to use this to start translating the problem a little bit. And so we're going to do this for the Boeing 737 and the Dash 8. So I started to draw a little bit of a diagram as to what was going on between their distances, the rate, and the time. So the red line represents the distance that the Boeing 737 is traveling. And notice that I haven't put anything in for D because I'm not sure how far it's traveled. I know it has a cruising speed of 500 miles an hour, and I've left the T because I don't know how long it's been traveling. And I've done a similar process for the Dash 8. Again, I don't know how far it's traveled, so I've left it as D. I know it has a cruising speed of 302 miles an hour, so I put that in for the rate. And then for the time, I use T plus 1. Now, why use a T plus 1? Well, remember the Dash 8 takes off first, which means it's been traveling for 1 hour longer. So in terms of their time, they almost have the same time, but the Dash 8 has been traveling 1 hour longer. So after translating a little bit of the information into some formulas, I was actually able to see some more connections. And one of those was actually just their distances. In the problem, we want to know when the Boeing 737 actually overtakes the Dash 8. And one way that you can visualize what's going on there is you want to know when they will have exactly the same distance. You know, when will that Boeing 737 actually catch up to the Dash 8? Well, since we want to know when they'll have the same distance, we can actually take these two formulas and set them equal to one another. Now, in doing so, then we actually have something that we can solve, because this equation here only has T in it. So I work to solve this like I do many of my other linear equations. I first want to get the T's together, and then isolate the T as much as possible. Well, to start this process off, I'm going to distribute through by the 302. This will give me 500T equals 302T plus 302. Now, if I subtract 302 from both sides, that will actually combine my T's. So 198T equals 302. And then in my last step, just go ahead and divide by 198. So I get that T is equal to 302 divided by 198. Now, right there, that may seem like a pretty good answer, but actually I'm not done. Because imagine this. If you're in that little Dash 8 and you radio the tower, you might ask them, hey, I got a Boeing 737 behind me. How long is it going to take until it overtakes me? And if the tower responds that it's going to take 302 divided by 198, then you're going to be a little confused. You know, what you really want to know is, well, how many hours is that, or how many minutes? You know, how much time do I really have before it overtakes me? And so in a problem like this, we need to rework the answer so it fits the context of the problem just a little bit better. So to help with this, I'm first actually just going to punch it into a calculator so I get the decimal approximation. So T is equal to about 1.53. And then I remember that this is actually in hours. So it's going to take the Boeing 737 about 1.53 hours to overtake the Dash 8, or say about an hour and 30 minutes. And in that way, it fits the context of the problem much better. For this next problem, we're going to look at something just slightly different and start working in those ideas of linear inequalities. So in this one, we have that Sandy is hiring a painting company in order to paint her home, and that the company basically has two plans that she can choose from. In Plan A, it will cost her a flat fee of $250 plus $10 per hour. In Plan B, there is no flat fee, and they just charge her $20 per hour. And so the question is, when will Plan B be more expensive than Plan A? Now, on the surface, it may not seem like this is a good application of an inequality, but actually it is. Because there's not going to be a single spot where Plan A or Plan B is going to be more expensive. Instead, it's going to be a whole range of hours where Plan B will be more expensive. So we're going to take the cost of each of these plans and set them up in an inequality. You'll notice in this one, on the left, I've set up the cost of Plan A. So X represents the number of hours the job will take. So $10 per every hour plus the $250 flat fee. And on the right, we have Plan B, which is just $20 multiplied by every hour. And since we want to know when Plan B will be more expensive than Plan A, that's why I have basically that Plan B is greater than Plan A. So we work to solve this much like we do our inequalities. Work to get the x's together and then isolate it. So in my first step, I'm just going to basically subtract a 10x from both sides. Then, go ahead and divide both sides by 10. And since we're dividing by a positive number, that won't change the sign. So what we have here as our answer is that x is greater than 25. And of course, remember to put this back into the context of the problem itself. So what this is really saying is that if the job takes more than 25 hours, say 30 or 35 or even 40 hours, that plan B will be more expensive than plan A. Now that you've seen these three examples, you might have a better idea of how linear equations and inequalities can fit in the context of more of a real problem. But of course, you also might have a few doubts in your mind and say, well, these problems are a little bit cooked up. I'm not sure that linear equations are necessarily going to be helpful in everyday life. Well, there are situations where you can take some very real data that's not quite a linear relationship and still fit a line to the relationship anyway. And in these instances, you can still use a linear model to predict future data points. Now, the mathematics behind this process is usually one for statistics, and so we're not going to necessarily cover the nuts and bolts of how this equation gets formed. But with the aid of, say, a graphing calculator, we'll be able to do the process just fine. So let me show you what I'm talking about. In this example, I basically have a whole bunch of data points that represent the number of U.S. households with cable television. And so in the table, basically I have all the years listed out from 1999 up to 2006, and then the number of people or subscribers in millions that have cable television. Now, if you look at the scatter plot of this data, you can see that it's not exactly a line. You know, some data points are higher or lower, but it does look really close to a line. And so if I was in the business of the cable industry, I might be really curious as to some of those future data points. You know, how much can I expect to have in terms of subscribers for the year 2012 or even 2015? You know, what are those future values going to be? So what we're going to do is we're going to fit a linear model to these data points using the process of linear regression. To do the process of linear regression in this class, you really do need a graphing calculator or, say, a computer in order to take care of creating that line. Now, if you do use, say, a calculator or even a computer program, the process is pretty much the same. First, we want to take all of the data in the table and enter it into the calculator, then use its statistics feature to actually create that linear model. Then we'll go ahead and look at the return values and try and interpret what it's giving us. So let's go through these steps one at a time. The first step is I'm basically going to take all of my data and enter it into the calculator. And most of the time, if we do have something in terms of years, we like to scale that back to some smaller data points. So instead of using 1999, I scale that all the way back to 0. And my x values become the years after 1999. That's why in my table you see stuff like 0, 1, 2, 3, 4, 5, and 6. And so we'll have to be careful when interpreting this later. I also enter in the number of subscribers as another column in my table. That way it's all nicely stored inside the calculator. Now that all the data is entered in the calculator, I want to have it go ahead and make my linear regression line. So I'll go into the stats feature of my calculator and find the linear regression option and then tell it to use my table of data. And usually the calculator just takes a little bit of thinking and then it returns some values in terms of what the regression line is. And the way you want to interpret these values is extremely important. The A value on my calculator represents the slope. The B value would be the y-intercept. And then it gives an R2 and an R. Those values down there have a little bit to do with how well the line fits the data. And so for the last one, the R value, that's known as the correlation coefficient. And the way you want to think of that one is that the closer it is to 1, the better it fits the data. So what my calculator is actually telling me here is that it fit the line to the data, and the equation of that line is y equals 2.86x plus 76.74. So there I have my slope and I have my y-intercept. So if we interpret this equation correctly, we can start doing a little bit more work with it, like predicting future amounts. If you want to start interpreting some of the values like the slope and the y-intercept, the slope is basically telling us how many more millions of subscribers you get per year. So it looks like every year you're getting about 2.86 million more subscribers. Now the y-intercept, that corresponds to when x equals 0. And remember, when x equals 0, that represents the 1999. So this says in the year 1999, we had about 76.74 million subscribers. All right, let's go ahead and start making some predictions with this. Suppose I want to predict about how many subscribers we'll have in the year 2010. Well, now that I have my model, I basically want to substitute in the value x equals 11, because x equals 11 corresponds to the year 2010. Well, when you plug 11 into our linear equation, it predicts that we'll have about 108.2 million subscribers in that year. So we'll go ahead and fit that into the context of the problem and just basically say that we'll have about 108.2 million cable subscribers in the year 2010.